In this clip, I'll discuss a few creational design patterns. In particular, we'll look at the singleton and object pool patterns. In the Design Patterns book, the authors distinguish three categories of patterns. The first is a set of behavioral patterns that try to capture the way in which classes or objects interact. Examples of behavioral patterns are the observer pattern and the strategy. Structural patterns deal with the composition of classes or objects. Examples are the adapter, the bridge, and the decorator. Finally, creational patterns are concerned with how objects are created. We've already seen one of them, the abstract factory. Thinking about where objects are created is important. We've looked at various ways in which classes work together, encapsulate variations, and hide implementation details. The counterpart of hiding implementation details is that somewhere in the code, objects still need to be created that contain these details. What factories do is to separate object creation and usage. This leads to stronger cohesion, because methods have less responsibilities. In the case of the sales order example, we use the factory to create country-specific tax, language, and shipping rules, so that the order object no longer has to take care of this. The GRASS principles also mention this creator role. Larman says that overall, if a class A has an B object, it's the responsibility of A to also create that B object. This works fine if B is a direct implementation of something. If it's an abstract class, so if you're programming against an interface, you may want to improve your design by applying creational design patterns. As opposed to Larman, Shalloway and Trott argue that an object should either make or manage other objects, or it should use them, never both. If you follow this rule, it leads to looser coupling. There are already design patterns for using an object. Program to an interface, not an implementation, means that you should introduce an abstract class. This abstract class encapsulates any variations in the objects that you use. As a result, the object using the implementations via that abstract class doesn't need to know anything about the actual implementations. The strategy is a good example of this. The context doesn't know anything about the concrete strategies, because there's an abstract class that encapsulates that variation. The problem is that if the context is also required to create these concrete strategy objects, it still needs to know which concrete strategies exist, and that breaks the abstraction barrier. To solve this, we need to assign the responsibility of creating the strategy objects to another object. When you use something like an abstract factory, the context will use a factory object instead, and then this object is responsible for creating the right objects. We've seen this in the sales order example, where we have a factory object for each country that creates the right strategies for taxes, languages, shipping, and so on. The factory creates objects on request, and the class that uses these objects, the context, knows only about the interface and not the implementation. And the other way around is that factories should only be concerned with creating the objects and not rely on any details or other methods of the abstract class, since that is the domain of the context that uses the objects. If you have a structure like this, you can add new concrete classes at any point, and you don't have to change the context at all. In the case of sales order, if the tax rules for a particular country change, you only have to update the factory object for that country. Sales order itself doesn't have to change at all. This is the open-closed principle at work. Patterns, such as strategy, hide information behind an abstract class. This makes the code easier to maintain. but also adds complexity, because the client code needs to know how these structures work. Factories and other creational patterns help hide this complexity, since you don't have to create the actual objects yourself anymore. Until now, we've only seen factories that simply create the concrete instances that are needed. But you can also add constraints. For example, in some cases it's useful to limit the number of instances that's available. The singleton pattern is an example of a design pattern that guarantees that exactly one object exists of a particular type. This is what it looks like in UML. There's a method called getInstance that returns the instance of the singleton. And the constructor is private, so you can only access an instance via the getInstance method, and you can create it yourself. Note that this UML diagram is a simplification, and whether this structure works or is needed at all depends on the programming language that you use. For example, if you want to create a singleton in C++, you need to do more, because C++ allows for multiple constructors, you can overload operators that return new instances, and so on. A singleton like this in Python is not even possible, because Python doesn't have access modifier to control who can call a method. In Python, you can use modules instead, which are basically singletons already. If you don't need to store any data, you can define the functions that you need in a module and export those. If you do need data, you can declare variables in the module that precede their names with an underscore to indicate that you're not supposed to use them outside of the module. If you really want singletons in Python, you can do it like this. But honestly, I don't see the need. Singletons, or modules, are used for objects that are shared in the entire application, and you only need one of them. Logging services, event managers, or texture managers are good examples. There's discussion about whether the singleton is really needed. Also, if you rely too much on singletons, this introduces coupling in your application, because lots of parts are now dependent on the singleton and its methods. Another potential issue with singletons is that they don't work well with multi-threaded applications. If two threads ask for a singleton instance at the same time, you may accidentally create two instances instead of one, leading to all kinds of trouble. In my opinion, avoid them and use other language features such as modules in Python that achieve the same thing. There are more possibilities than simply creating objects. Let's look at an electronic banking case study. Suppose that you want to write software that provides an online investment service. Customers can browse their investment portfolio and give orders to buy or sell certain stocks. Your service uses a broker that places and executes these orders for you. This is what the architecture looks like. There's a website that the customer logs into and interacts with. Your backend exposes a REST API to process requests from the website. And finally, your backend connects with the broker using a WebSocket connection. The broker uses WebSockets because they are the fastest way to get stock market information. A WebSocket connection is continuously open, but there's a limit to how many requests you can push through the WebSocket. And there's also a limit to how many WebSocket connections you can have to the broker at the same time. Your backend is responsible for checking that a customer request is allowed, and it translates the request into orders that the broker system can understand. Here's an example of such an interaction. Say that the user places an order to buy a certain stock via the website. The backend gets this request via its API, and it creates an order request that the broker can understand. The backend then uses a WebSocket connection to send the request to the broker, who then accepts it, buys the stock, and sends back a confirmation. There are some performance concerns. Your backend should be able to process many of these requests at the same time. But there are limits to what is possible for a single WebSocket connection. We have to create a system that can handle as many transactions as possible at the same time, while also taking into account these limits. This means we're going to need multiple WebSocket connections. One connection is not enough to handle the traffic, but 100 is above the allowed bandwidth we have from the broker, which is 20 connections maximum at the same time. We need a good solution for this, because without solving it, our system will be highly unpredictable. What are the problems we need to solve? We need code that can establish a single stable WebSocket connection. We need to determine the number of connections that are actually needed. And we need a way to load balance these connections. We don't want to route all traffic through a single connection when the other connections are not doing anything. So what to do first? As a first step, you can start by creating a single connection. In other words, we start with a single responsibility. And then we also need to design the system so that we can easily change the number of connections that is used. This is another responsibility. We separate these two responsibilities by creating two classes. A connection class that's responsible for communicating with the broker via a single WebSocket connection, and a connection manager class that's responsible for keeping track of the open connections. In this design, we'll have multiple connection objects, one for each WebSocket connection. And there should be only a single connection manager. For the connection manager, you can use the singleton pattern if you like, or create a Python module. The connection manager needs to maintain a list of connection objects. It needs a method acquire connection that looks through this list and finds an available connection. If no connection is available, it should wait for a bit and try again. And a release connection method tells the manager that the connection is no longer needed and can be used to process another request. Transacting with the broker is now pretty straightforward. You first ask the connection manager for a connection object. You use that object to perform the transaction with the broker. And finally, you release the connection again to the connection manager. The code that uses the connection doesn't need to know anything about how many connections there are, how they are created, and so on. As a result, this solution has strong cohesion and loose coupling. The API endpoints, the connection, and connection manager all have clear responsibilities. You can now also add error handling in the right spots. For example, what happens when a connection goes down? The backend needs to request a new connection. The connection that went down should be closed, and the connection manager might want to establish a new connection automatically to replace the one that went down. If the system is handling millions of dollars of transactions, you might want to do more than this. The connection manager could periodically check that each connection is still valid. For example, every 15 minutes, you could check for unanswered requests from a connection, query connections whether they're still available, check if connections have run into an error, and so on. If you detect any problems, you could inform a warning system that something needs to be done. You can go even further and log all the transactions of the system, so you can also detect other kinds of problems and trace back from the logs to see what happened. The pattern you just saw is called the object pool, or reusable pool. This creational pattern gives you the possibility to have control over how many instances of a certain class are allowed at any point. So as you can see, factories can do much more than simply create an instance of a class. Here's an object pool joke, and the objects are alligators. A millionaire loves alligators and has a pool filled with them. One night, he throws a party and says, "Whoever can swim from one end to the other of the alligator-infested pool unharmed will get a prize. One of my cars or $1 million. Some people line up, but they are hesitant. One man, though, gets in the water, swims from one end to the other unharmed, and goes to the millionaire. The millionaire says, "Whoa, I can't believe you did it. So what's your prize?" The guy says, "I don't care about the $1 million or your cars. I just want to know who the bastard was that pushed me into the pool." This is the end of the clip about the object pool. In the next and last clip, we'll talk about a few more useful design patterns. Please post any questions you have in the Teams channel of the course. Thanks for watching, and catch you in the next one.